Hi guys, Dr. B here. This is topic 6.5 AP Chemistry, Energy of Phase Changes. The objective is to be able to explain the changes in heat absorbed or released by a system undergoing a phase transition based on the amount of the substance in moles and the molar enthalpy of the phase transition. So it says you don't really need to use an equation, but I suggest you write this one down. Q equals mass or moles times delta H, or the enthalpy of the phase change, which is going to be what you're going to see what I'm talking about in a minute. So we can calculate the heat released or absorbed when a phase transition takes place. There is no change in temperature during the phase transition. The energy is used to change the position of the particles relative to one another. In other words, the potential energy is changing. This is shown as the plateaus on the heating or cooling curve, which you should have seen before in sophomore year chemistry. So the segment for boiling is longer than melting, therefore it's implying that more energy is separating the liquid particles to form a gas compared to solid state to a liquid state. To calculate the heat needed to perform a phase change, whichever it is, we can use the enthalpy for that phase change and multiply by the amount of material. So this is the equation I wanted you to write down. Q equals the mass or moles times delta H. Q is the heat, mass or moles is M or N, and delta H is the enthalpy of the phase change. So you may see heat of fusion, heat of vaporization, whatnot. So we talk about endothermic and exothermic reactions. So endothermic heat is absorbed from their surroundings to the system, while exothermic heat is released from the system into the surroundings. Through the different phase changes, you have solid, liquid, gas. When we're looking at solid to liquid, you may see fusion, you may see crystallization, freezing, melting. Going from liquid to gas is boiling and vaporization, condensation, depends on which direction you're going. Sublimation and deposition we've talked about before. So, given the heating curve for mercury, calculate the heat to freeze 100 grams of mercury at its melting point. So we're talking about melting. If I tell you that the melting point is 234 Kelvin, that doesn't really impact our calculations because we're trying to find the amount of heat needed to freeze. So we're going to use Q equals the mass times delta H fusion. Notice, however, the heat of fusion here, because we're trying to do freezing, so that's fusion. Notice how it gives us 2.30 kilojoules per mole. What does that mean exactly? You're going to have to convert. Q equals your mass, 100 grams, times 1 mole over the molar mass of mercury, which is, where is it? I don't see it. 200.59 grams. That's in my moles. Multiply that by my heat of fusion, but because this is an exothermic reaction, heat is released. Because we're talking about freezing, we're going from liquid to solid, heat is released. So that means heat is leaving the system into the surroundings, so my heat of fusion will be negative. So negative 2.30 kilojoules per 1 mole. So I do my math, I will end up with negative 1.147 kilojoules. So if you're curious about sig figs, why did I pick this one? It's because the heat of fusion and the molar mass are all constants, so I don't have to worry about that. The number of sig figs will come from the problem. Aluminum melts, freezes at 933 Kelvin. How much energy is required to freeze 2.50 moles of aluminum at 933 Kelvin. We're given two things to work with. We're given the heat of fusion and then the heat of vaporization. So just so we're clear, heat of fusion is solid to liquid or vice versa. And then vaporization is liquid to gas, vice versa. So we're talking about freezing. So we're going to be looking at the delta H fusion. However, it says to freeze, so we're from liquid to solid. Again, heat is released. Therefore, my delta H will be negative. So we have Q, we have moles, and we have our heat of fusion in moles. So let's just use this one. Q equals N times delta H fusion. So my Q is going to be my number of moles, which is 2.50 moles, times negative 10.9 kilojoules per 1 mole. So my moles will cancel out, I'm left with kilojoules. Negative 27.3 kilojoules. All right, that's it. If you have any questions, please let me know. Thanks.